you know the topic, small language models, how they will help you survive agentic AI. I wanted to ask you questions before my talk. Who of you have attended more than 3 agentic talks today? More than 2? More than 1? The numbers should be higher. All right. So I would say 50% of you have already have listened to an agentic talk. For the rest of you, this will be the first time at this conference to hear about agents. If you traveled 150 years ago in California, you would see an ad like this, promising you the riches during gold rush, promising you better life. If you go to the Bay Area today, you'll see something like this. Salesforce trying to sell you Agentforce. Companies like FinAI selling you customer agents. And even Postman is asking you whether your APIs are ready for agents. Even smart people like Satya Nadella from Microsoft has recently said that AI agents will become the primary way of interacting with computers. How do we survive all this madness? I will summarize my entire talk in these 3 bullets. So if you need to catch a flight or want a coffee, you can leave immediately after. The TLDR of this talk is get your hands dirty, use the tools that we'll share in this talk, test the ideas on your laptop, and start using small language models as a way to learn. All right, let's get into the depth of the content. A little bit about myself. I started out at Google working on a streaming analytics solution called Cloud Data Flow. I then went and broke a few things at Snowflake. I literally broke a few things at Snowflake. At one point, valuation of Snowflake decreased by $10 billion because of a product that I launched. The product was a performance improvement. So obviously, the usage of Snowflake decreased. And then I went and broke more things at Databricks, working on things like dedicated clusters and serverless filtering and Unity Catalog. All actually very interesting, beautiful things. Now, today I'm working on a product called Tower, or a startup. I'm a co-founder in a startup called Tower. We are an orchestrator for Pythonic data flows. We also give you the compute to run these data flows. And if you need, we can also give you the managed storage, analytical storage, based on Apache Iceberg. I will try to limit my commercials to the minimum, but there will be here and there some mentionings of Tower, because this is an area that I'm passionate about. We basically built Tower to allow you to do things that are here, that I will be talking about. So for the rest of the time, I wanted to spend my 35 minutes or 30 minutes checking how we ended up with equating LLMs with autonomous intelligence. It was an interesting journey. Then I will compare LLMs versus SLMs, small language models. And then I'll give you some tips and techniques to use SLMs to experiment with agentic workflows. The last 40 years of humanity can be summarized in this one quote from Mr. Eldron Tyrell, CEO of Tyrell Corporation, that we want to achieve autonomous intelligence, and we want to build things that are more human than humans. In 1995, 2 smart gentlemen wrote a book, the Artificial Intelligence book, which is the SOTA of the space. Many students learn about artificial intelligence based on this book. And they defined an agent as an entity that does 4 things. It perceives its environment, it makes decisions, and takes actions to achieve a goal. So I try to break it down into these 4 things. There's a goal that an entity wants to achieve. It perceives the context, makes decisions by making actions or taking actions. Now, LLMs is not the first attempt of humanity on creating this autonomous intelligence. We used to have classic agents with techniques such as utility theory or reinforcement learning. Your 20-year-old elevator, or 30-year-old elevator, Schindler, Otis, used to have decisioning in it that optimized travel times in a high-rise. Now, about in 2020, as vendors were training more advanced language models, something very interesting happened. Specifically, the reasoning chains that were embedded in the training data in Stack Overflow or on forums or in the code bases, it started seeping into these language models, in effect creating reasoning patterns. Now, this was not enough yet to make an LLM a reasoning engine or a decisioning engine. 2 years later, another set of smart folks came up with this concept of chain of thought prompting. And the idea there was we should, in our training data, incorporate not just the input and output, but also incorporate the reasoning steps, the intermediate steps. And so together, these two advancements created or made LLMs decisioning engines. LLMs became brains, so let's use them. In the new world of language models, agents, you still have the goal and perceiving the environment and making decisions and taking actions, but now agents do these actions by perceiving the environment through the output of tools and by looking into memory. Then making decisions is happening through a reasoning loop, and actions are being taken by calling tools or functions. To illustrate how all of this works, the combination of a language model and the ability to call tools created agents. That's what an agent is. There's a language model inside, and the language model produces the decisions to call a tool. Tools are being called. Output gets routed back. Let me actually follow the diagram here. So there's a prompt. A user asks the agent to do something. First, this prompt gets decomposed in subtasks. This is the reasoning process. To accomplish each subtask, tools are being called. They can call an API. They can get data from an analytical database, from an operational database. And then only when the language model outputs a very specific token, it's the final answer token, the process ends for that prompt. The prompt and the output get stored in a concept called memory, and the cycle begins again. All right. Now, someone very smart, not me, said or thought about language models, large language models, actually being an overkill for the purpose of reasoning. And the best way to think about it is this. Do you need, if you're trying to decide whether to go left or right on a highway, do you need to know who the Queen of England was in 1600s? Probably not. So an agent is very similar. It needs to make a decision, call this tool, that tool, or another tool. Why would they need to know who the Queen of England was in a particular year? So this irrelevant knowledge that is embedded in a large language model is not necessary. And because, so this is point number 2 in the slide. The first, another reason why large language models are not necessary is their large sizes makes inference very expensive. And because it's expensive, it requires sophisticated hardware. Sophisticated hardware needs to be usually available in the cloud. So you're limited only to language models deployed to the cloud. Therefore, experimentation becomes very difficult or more difficult than it needs to be. So 4 months ago, NVIDIA and Georgia Tech published a paper that stated that small language models are the future of agentic AI. Now, what does it mean, small? There are a couple of definitions of small. Some folks like to use a particular number of parameters. I like a different definition of small. Whatever fits the memory of a consumer device, a laptop or a phone. This year, this size is 16 gigabytes. Next year, it might be a bit larger. This definition allows us to scale as we go. But the definition also means, typically, small means you have a model of about 10 billion parameters or less. Although cheating is allowed, you can use more models with more parameters as long as you use a version that's called a quantized version of a model, or maybe a distilled one. The strength of small language models is that data doesn't leave your device. You gain privacy benefits by using small language models. You can also train these models on specific tasks. And as you will see a little bit later in this presentation, there are really just 4 tasks that are important for agents. It's being able to call tools. It's reasoning. Reasoning means subdividing a goal into subgoals. It's generating glue code, and it's following instructions. So in reality, these are only the 4 things that are necessary for an agentic workflow. And you can train a model to do it better than a generalized model. Now, the downside of a small language model is that it hallucinates facts. It doesn't know who the Queen of England is, but perhaps that's not important. So the authors of the paper also made some statements. I'll keep it brief. They claimed, or they stated, that SLMs are now sufficiently powerful to accomplish these 4 tasks: code generation, tool calling, instruction following, and reasoning. And because they're smaller, they're also more flexible. They can be deployed either on this machine or on your desktop or in your cloud, on your on-premises devices. So you gain more flexibility. And of course, they're cheaper to operate, cheaper to run inference on. Now, I already told you what the four important qualities are, but here they are again summarized. The 4 most important qualities of a language model as it relates to agentic workflows is the ability to break down your goal, your task, into subtasks. This is what's called reasoning. Then being able to call functions or tools. And here, what's important is parameter passing and creating output that can be interpreted later on in the loop. Generating glue code, because your agent will not always have access to all the tools to accomplish a task. There will always be a need to generate some extra Python code. And lastly, following instructions that go into your prompt. There's a comparison in this paper. I'm not going to go line by line, but the summary of the gist of this comparison is for the major model families available today from Microsoft, NVIDIA, Hugging Face, Salesforce. These small language models, they typically are between 1 billion and 9 billion parameters. They achieve accuracy in the 4 specific tasks that rival the accuracy of much larger models. There's also a leaderboard. Who heard about the Berkeley function calling leaderboard? You guys encountered it? It's a pretty famous one. Pretty much every vendor tries to benchmark their models on this leaderboard. It's specifically for agentic workflows. There are 111 models listed there as of November from all the major vendors. And I wanted you to pay attention to the cost column. The top models are actually still the large language models. They all have hundreds of billions of parameters. It's a bit of an exception at the top of this ranking. It's the xLAM model. It has 355 billion parameters, but they use the what is called a expert architecture. So they only activate a subset of these parameters. And that's why the cost of inference is actually relatively reasonable. Unfortunately, it's not open source. And unfortunately, it's also not deployable to your hardware device because the overall model is 355 billion parameters. So we can't use it for our experimentation. All the other good models here cost hundreds of dollars per benchmark run. So Claude Opus costs $207 per that run. Claude Sonnet is $43. Grok 4 is $363. Now compare this with the next small language model, which is actually Claude Haiku. You can call it that. It costs reasonably. It's more reasonable in costs. Unfortunately, it's not open source. You can't really deploy it on your device. So we'll remove it from comparison. The next model that is highly ranked, so it's number 20 out of 111, is a model that is open source, small, can be deployed to your device, and does pretty well on accuracy and in practical life. So this is the model we'll use in the demos in the stock. It's the Salesforce xLAM 2 32 billion parameter model. I'm using the 4-bit quantized version so that it fits my laptop. I have a relatively, well, say average device. So it's nothing high-end. But it runs, so it's the beauty of these models. The same data represented in a cost versus accuracy comparison kind of tells you the same thing. The top model is the GLM model, but it's large, 355 billion parameters, cannot fit any consumer hardware. And the middle rankings is the xLAM series, xLAM 2. It gives you a good balance of accuracy and cost. If you wondered how these models were trained, how the xLAM 2 model was trained, it's actually a process of fine-tuning. They took an existing large language model, actually 2 of them, Llama 3 for one set of versions, and Qwen 2.5 for another set of versions. And then they also generated a synthetic data set of tool calls. And this is the secret sauce of the process. Salesforce created a tool that generated 60,000 examples of tool calls. The input was a human query, do something, do XYZ, and the output was a tool call. And they used this data set to fine-tune the large language models, and they ended up with Salesforce xLAM 2. So no magic in the world, everything is explainable. You can actually go and do it yourself if you have the time. So the benefit of SLMs for agents can be summarized in they cost less to run inference on, therefore they're more flexible, can be deployed on any device. Cloud is optional, therefore it enables experimentation. You can start with your development hardware and you can promote it to cloud hardware once you're ready to go in production. So, are we now ready to survive and use SLMs to survive the agentic AI hype? Let's science the shit out of it. Your setup will consist of 5 things. We'll use a SLM. We recommend the Salesforce model xLAM 2, the 32-bit billion parameter model, but quantized. If you would like to use something else, you can also, we've seen some pretty good results on the open source version of GPT, the 20 billion parameter edition or version. Now you'll need something that's called a local inference server for local experimentation. The local inference server is basically a server that runs on your laptop or on your desktop and that answers queries, answers prompts. And it runs inference on these language models. We recommend Llama CPP. There are other options, LLM or Llama. I'll compare them and explain why we recommend Llama CPP. Now, eventually, you'll probably want to run these agents in production. Your laptop will not be enough. You'll probably want to use an inference service. You can also get your own hardware and rent a VM with GPUs. But if you want to start with maybe something easier, an inference service will be quite useful. Together AI is great, Hugging Face we had good experiences with, and you can use OpenAI. Now, there's another tool that might be useful for you, especially for the development part of it. It's a Python runtime service. What's the benefit of a Python runtime service? It allows you to easily move applications from one device to another device, keeping the same format for your apps. It also gives you some observability benefits, some logging and metrics benefits. You can use Tower, or you can use Model or Fly.io. And lastly, to save time and trouble and tears, I recommend using an Agentic framework to develop against or to develop with. We like LangChain, but there are other options as well. For example, Llama llama index. So why did we choose, why do we recommend llama CPP? That's an open source tool, by the way. The three options you see here are all great. We all tried them. In practical terms, once you start trying to run local inference servers, you'll have to kind of answer the question, are you a Windows person or a Mac person? If you are a Mac person, you'll probably want to use the GPUs of your Mac hardware, Apple Silicon. If you are a Windows person, that's not, this column is not important. But for those of us who, or those of you who are using Macs, it would be kind of a waste not to use the Metal capability of your development machine. Only 2 of these servers support Macs. Unfortunately, VLLM runs on CPUs when deployed to a Mac. It doesn't use your local GPUs. Therefore, your choices are either Llama CPP or Ollama. Now, another weird consideration that will become actually quite important once you start experimenting with different models is naming and naming conventions. There are by now probably hundreds of thousands versions of models out there, probably millions. And if you want to use a specific version of a model, you have to refer to it somehow. There's a standard created by Hugging Face that pretty much every other inference server uses, except Ollama. Ollama has its own little naming scheme. Llama CPP follows the naming scheme of Hugging Face. Therefore, it's the best inference server that we found, and we recommend using it. So try it out. Now, let me also show you what you can get by using what I mentioned as a Python runtime service. It's a development tool. It can take any Python code that you write. It gives you some SDK features like analytical tables or LLM model instantiation, or you can also instantiate dbt models. Tower specifically allows you to nicely package your app by just specifying the name of the app and parameters. It can take any code, Python code. You run this code the same way both locally and in the cloud. It has a self-hosted runner, so if you want to run it on a on-premises device, you can do that too. And lastly, you get a orchestration capability. So you have a scheduler and the ability to call other apps. That's all it does. It's a nice development tool, but it happens to save you a lot of time when you start developing agents. You're looking at a few features of Tower, self-hosted runners, and eventually you'll see some observability features as well. All right. So what else can you do in Tower? You can build boring ETL pipelines. You can build some interactive apps. You can also build some data agents and tools of these agents. And ultimately, you can build a data platform from ingestion into Apache Iceberg, transformations of raw data into more higher quality data, and presenting this data to your users in notebooks or agents. I mentioned Iceberg a few times. Who of you have heard of Apache Iceberg? All right, well, I'm pleasantly surprised. The news gets around. The reason why I think agents need access to fresh business data is exemplified by a case of 2 years ago when a New York law firm got in real trouble by generating a legal case using ChatGPT. And at that time, ChatGPT did not have the ability to call tools. So it only used the information that was in the training data set, which by the time of usage was already 9 months old. And so it generated some hallucinated case numbers. That was the state-of-the-art technology of that time, 2023. I think this case pretty much started the need for tool calling, or it kind of justified the tool calling improvements. There are other examples of, I think, an airline agent giving wrong information about airline policies. It was an Air Canada agent. So lots of these examples where language models only use the information contained in them at training time. So an agent using LM without access to fresh business data is a dumb agent. And a small language model will be even dumber because by definition it does not know even who the Queen of England was in 1600. So how can it know about the transactions of your business as of 5 minutes ago? The industry has been working on this concept of open formats, and the data industry. And the benefit to users is they start owning the data. The analytical data is owned by the end user, and users have the choice of choosing different compute engines. Some of these compute engines will do ETL. Some of these compute engines will run agents. And the beauty of this architecture is they all work on the same data. There's no ETL that is required to move data around. Tower, for example, is one of the possibilities in this architecture. You can use Tower for Python workloads. You can use Snowflake for other workloads, Databricks, Fabric, and so on. Now, let's get started. Let's start experimenting. Let's get to demo mode. You'll start by installing an inference server. Here's the command to install Llama CPP. And then you'll invoke it by specifying the model that you want to run. Here's a command for a version of xLAM 2. This is a quantized version of it, which only takes about less than 16 gigabytes of RAM. You'll write your agent using LangChain. I'll show you how. And then you can use, for example, Tower to run it, to debug it and run it in prod. So for the demo, I took a case of a data agent that retrieves information about stock prices for a particular day. So there's a set of stock tickers, Amazon, Oracle, Netflix. You give it a day, and the prompt is, what was the stock price of these set of tickers on that day? Now, the agent has two tools it can use. It can either go to its internal cache. The agent has a cache. It happens to be a lakehouse based on Iceberg. But if the data is not in the cache, it can go to an external service. We're using here for the demo Yahoo Finance. It will download this information from Yahoo, and it will store in the cache, and then return the data to the user. Now, the way you instruct the agent to do this work, and this is actually the difference, the main difference between agentic workflows and predefined DAGs. You define business rules, instructions. And these business rules can be use a human understandable language. You as a data engineer, you can go to a business user and you can define these rules together with them. They'll probably understand what you're talking about. So the business rules for my workflow are you can get stock ticker prices either from a database or you can fetch it from Yahoo. But getting it from the database is preferred because it's cheaper and faster. So that's kind of the extent. That's how you define some workflows in the future will be defined like this. Instead of code, instead of DAGs, you will have a set of statements, instructions. Now, how does the agent know which tools to call? It's actually quite interesting. If you use LangChain and you put a decorator tool on a function, LangChain knows how to extract the name of that function. It will extract the arguments of the function, and it will also use the docstring of the function, and it will all become the input in its system prompt, in its prompt. So here's a bit longer demo of doing inference and running this agent. So I just started Llama server. It's running locally on my hardware device, on my development laptop. I go and I write up an agent using LangChain. There are a couple of helper functions. The first one is creating an LLM. The other helper function is access to the database. Then I start defining my tools. The first tool is the checker tool. It's the tool that will check initially, is the data already in the cache? it will create the output if the data is already in cache. The second tool is a fetcher tool that will go to Yahoo and download the information if the data is not in the database. And we are using a feature of Tower that kind of can treat every Tower app as a tool. And then we go to my favorite part, where we define business rules. So these are the instructions. You can get stock price from 2 places, but please prioritize a particular place. And when you, and the kind of list goes on, I have 5 rules or 6 rules that I want the agent to follow. The rest of the code is boilerplate, creating an agent, passing the tools to it, and invoking. So let's see it run. Initially, I'll run it on my development laptop. I have the GPU history window open to show you. Okay, right now you're not seeing it, but now you're seeing it. So the local GPU is being used. The inference is being run on my local device. Data for Amazon is already in my cache. Therefore, I will not call the fetcher. But data for Oracle is not yet in my cache, and therefore I will have to call the fetch tool. Not me, it's the agent that calls them through the reasoning loop. At the end, I will end up with information for both Oracle and Amazon. And the local run will end. Now, I want to deploy this agent to the cloud because I'm happy with how it works. I'm ready to run it in production. So I type in Tower deploy. And then I run the agent in the cloud. As you can see, there's no -- local anymore. But I wanted to make it a bit more fun. I added a new ticker, Netflix. So now the agent needs to run this flow for 3 stock tickers, including Netflix. If all goes well, what will happen is the agent will skip Amazon and Oracle because it was previously retrieved. But for Netflix, it will have to call the fetch tool again. Let's see if it works. So it runs the checker for Amazon. Amazon is there. Oracle is also in the cache. Netflix is missing, and it will call the fetch tool. And at the end, it will summarize the output. So as you can see, I didn't create a DAG. I did not create a if-then statement or a loop. I wrote up a set of business rules, and it was enough for the language model to determine which steps to take one after another. So let me start maybe summarizing and getting to what's next. Hopefully I was able to show you that small can be powerful. We recommend starting with a local setup on your development hardware. Use some tools that we mentioned in the talk. Use open source models. Use open source frameworks. Some of you might be asking, why the heck couldn't we use a simple Airflow DAG for this? And to be honest, the answer is, yeah, we could have used it. It would have been a pretty simple DAG. That's OK. I think in the future, we'll continue using predefined DAGs, which are very deterministic. But we'll also probably come up with a new way of doing data engineering, where you can give your business users the ability to freeform, to define their data processing requests in a free form. They'll be able to ask questions like, what was the stock price for tickers? And then, well, not then, actually, before that, you as a data engineer, you as a software engineer, you will work with your end users to develop business rules. And you'll have a collection of business rules that you'll write with them and agree with them. And they will be good for several months, maybe a year. And these business rules will control the behavior and the boundaries of your workflows. So instead of defining these DAGs, the agent will create the DAG for you based on the previous inputs. And that is pretty much the end of my slide where. Happy to take questions. If you'd like to get in touch with me, here's a QR code to my LinkedIn. You can also send me an email. And we have 5 minutes to take questions. So please go ahead.
I loved your chat. I think so. We're a bank, and we're on a journey to what you would call data products. Okay, so we're a Snowflake shop and a Python shop. My hypothesis is that for this to be true, we need to think about the data products we produce in the future to make the world of agentic real. I'm just kind of curious with your experience, what you would opine on in that, in terms of what do we need to think about from the data side of things to make the agentic world outcome.
I like the question. So the question was, the gentleman is from a bank. They're thinking about using agentic workflows. What can they do now to prepare for that future world? I'm a person that likes singletons. Like I'll give you one recommendation. It might be wrong, but start preparing your data in this open table formats. Start storing your stuff in Iceberg or Delta. I mean, your Snowflake shop, therefore, you'll probably be better served with Iceberg. Snowflake has great support for Iceberg. They're one of the major contributors. They even have a catalog, open catalog. I mean, maybe there are other options for catalogs. Lakekeeper is a great one, Apache Polaris. So start storing your data in the format that agents can use. Of course, agents can also call your Snowflake directly, but I think the innovation for agentic workflows will happen elsewhere. Therefore, you want to give agents the ability to run on the data without relying on Snowflake. Okay, so I'm going to keep my recommendation at this because there are probably like 5 other recommendations I can make. But if you take something away from the stock, then make your data agentic by putting it into Iceberg.
Thank you. It's good to hear.
Maybe this gentleman then next, and then you next. Okay, go ahead.
Yeah, when it comes to local inference, do you have any advice when it comes to Linux people?
I mean, Llama CPP will work. You don't have the problem with. Actually, you don't have the problem of Apple hardware. I think all 3 servers that I mentioned in my talk will work on Linux. You still have the naming problem, so that limits your choices to either VLLM or Llama CPP. You're in a better shape.
Oh, really? I'm using Llama right now. Should I be using...
Oh, well, so the reason why I started with Llama and then I ran into naming. So the reason I would maybe not recommend Llama at this time would be they use this proprietary naming scheme for models, which prevents you from downloading models from sources like Hugging Face. Only for that reason, I would recommend maybe using Llama CPP.
Oh, cool. I've heard of it, but never touched it. Thank you.
Sounds good. Maybe this gentleman first, and then you.
Okay, so I just one question. Great talk first. So currently, many small model maybe struggle with tool calling procedure. What's the strategy you can improve this tool actually calling without escalate the model size?
Yeah. We ran into it ourselves. If you listen to some vendors, they will tell you 8 billion parameters models are enough. And then when you try to run them, they enter into never-ending loops.
Yeah.
And they also try to call every tool they have access to.
Yeah.
Because it's how they trained. It's safer for them, for these language models, to overcall than undercall.
Yeah.
There are a couple of techniques you can use. The technique we ended up using was, we actually ended up with what traditionally would not be called a small language model. We used the 32 billion parameter model of xLAM 2, but we used the quantized version of it, which still fit into the memory of our devices. And that's why I like the definition of small as being whatever fits into your average consumer device. I don't like the number of parameters definition of small. So use maybe slightly smarter models, like 30 billion parameter models. There's a set of other techniques you can use, such as reducing temperature down to 0 so that the agents don't go crazy. You can do things like limiting the number of iterations, which is not great because in effect you are creating a stop to your loop, but it's a way to control it. And there are a few other things you can do. But what solved the problem for us really was going with the higher quality accuracy model, the 32 billion parameter model, and just quantizing it and using that.
Thank you.
Yep.